I'm Scott Tracy, and Bill Denayo, who will be stepping up here, we will be introducing the award recipients for the Science of the State Science Fair at Winnipeg. We've been doing this for over 35 years. Because I've been doing it for 5 years. And the award, the Charles H. Hammond Memorial Award for Excellence Astronomy, is designed to showcase or give students an opportunity who have done something in astronomy or encourage them to do a project in astronomy that involves basic research, some hands-on, and to solve a problem. If we choose them for an award, then they graciously come share what they did with us. And for those of you who have been around, there are years where we have not had any students doing an astronomy project. So we've had to kind of look for collateral topics that feed into astronomy. This year has been a good year. We have 2 excellent student presentations. The one that I will be introducing, Mia Jakubowsky, actually did not make it to the finalist section of the State Fair at Quinnipiac because they didn't have judges available that could look at hers and other projects. Fortunately, since we award a special award, we're in a special awards category, we can step out of that and choose anyone we wish who is part of the science fair. And since Mia's abstracts and her information were all up to be seen and previewed by those of us who were judges, Bill and I said, yeah, we got to look at this one. And fortunately, things have worked out. And so Mia, with us tonight, and thanks for the 2-hour drive to get here. Mia is a junior at the King's School in Stamford, Connecticut, and is well resourced to take care of this project. And actually, I have done enough talking. I'm going to let you introduce the project, and I think we should give her a warm ASGH for her.
Thank you so much. Hello, my name is Mia Jakubowsky, and I have been graciously invited to present a research project that I've been working on for a little over a year now. First and foremost, I want to thank ASGH for the honor of receiving the first place senior award at the Connecticut Science and Engineering Fair. As you're going to see, my project is centered entirely around amateur astronomers. So the fact that it resonated with your organization meant so much to me, and I really hope it resonates with all of you. So before I get into the nitty-gritty of my research process, I want to give you a very broad strokes overview of what my research was about. So my research was centered around the study of exoplanets. And to break down my rather complicated title on my poster, I created an equation, basically, in my project to help amateur astronomers predict which exoplanets they can detect based off of their equipment and observing conditions. I then took that equation, used Python to code it into a model script, and then kept working to make that script user-friendly to theoretically be usable by any astronomer, no matter how much research experience they have, no matter how much experience with exoplanets they have. So yeah, that was my overarching goal. I also want to talk a little bit about myself and what led me to do this kind of research. So I'm an 11th grader at King's School in Stamford, Connecticut. While my school doesn't have an astronomy program, we have an incredible science research program that basically pairs high school students like myself with professional laboratory settings. So I was paired with my mentor, Mr. Elgin Leary, at the Barnes-Bristow Observatory in Simsbury, Connecticut, which gave me the resources necessary to do exoplanet research. Before I even started my research, I took an introductory astronomy class at Brown University over the summer. And that's really where my passion for research and astronomy grew. For many years, I had loved astronomy, but more as a passion. Really, that course solidified for me that real research can be done and should absolutely be done in the field. Past just astronomy, I engage with science every day. I've been the leader of the Science, Technology, Engineering, and Math Club, or STEM Club, at my school for 3 years. And I tutor middle schoolers to try to share some of my passion for science and math with them. So I want to talk also a little bit about why I chose to pursue exoplanets specifically. Now, there are a couple different reasons. The first one was personal interest. It has always been so fascinating to me that entire worlds, sometimes much like our own, exist light years away in the universe, and we simply know nothing about them. So, it's always been a very personal interest of mine, discovering what other planets are like out there in the universe. Additionally, when I was talking to my mentor about what routes we could go down for research, it came to my attention the incredible scientific significance that exoplanets have. I'm sure, as you all know, as astronomers, exoplanets help us learn how solar systems form, what the universe looks like beyond our solar system, and it helps us learn about what our places, what Earth's places in the broader universe. Exoplanet research led scientists to the conclusion that our 8-planet solar system is very unique, and most exoplanet systems only have 1, maybe 2, sometimes 3 orbiting planets, but our solar system is incredibly unique for that reason. So it is a very significant field scientifically. And then the last and most important reason we chose to pursue exoplanet research was how easy they are to research. Essentially, if you have a telescope, a camera, and then some kind of tracking equipment, you can perform exoplanet research. And that's sort of the point I'm going to be getting at in my research, centered around amateur astronomers helping people who maybe have access to those resources actually participate in research. So next thing I'm going to talk about is the initial steps behind my research project. So when I first started out, I was a complete beginner. I had a wonderful mentor who very much showed me the ropes, showed me the possibilities of research, but I had no background, not even in astrophotography. I knew nothing about imaging. I did not know how to work a telescope, a camera, set up the observatory, nothing like that. So I did a tremendous amount of outside learning. I read and annotated papers. I read textbooks, particularly found helpful the handbook on CCD astronomy. It taught me so much about how you image and the science behind imaging, taught me how to take calibration frames, etc. The most important part of my background research, though, was identifying gaps in knowledge. So I was looking for, in my reading, what do we not know about exoplanets? And I actually identified 8,000 gaps, which are the 8,000 exoplanet candidates. Now, exoplanet candidates are stars that NASA thinks potentially could have exoplanets, but they're not confirmed. So maybe there's 1 or 2 data sets suggesting a potential exoplanet, but we don't know if it's there. And individual astronomers like myself and all of you actually have to go out and figure out if the exoplanets are there and then do the research. So from that catalog of 8,000 exoplanet candidates that I found, my research goal became discovering exoplanets. So you'll see how that goal kind of shifted as my project continued, but that was my initial setup. So the next thing I had to do was build a pipeline. Like I said, I had no experience, so I learned how to collect data, again, thanks to my mentor. At the observatory, we use SharpCap for imaging, so I learned how to use that software along with more software for data reduction and cleaning. Primarily, I use IRIS, which I don't know if any of you are familiar with it, but it was incredibly difficult to use as a beginner. Definitely not very user-friendly, but I made the best of it. I made it work, and it got great results. Some setbacks that we faced along the way. There were a lot of equipment setbacks. So I was working at the Barnes-Bristow Observatory in Simsbury, Connecticut. The equipment there is definitely amateur grade, and before my research was with exoplanets there, none of that equipment had ever been used for research purposes. Quite frankly, a research pipeline did not exist at that observatory. So with the help of my mentor, we built one. Some setbacks that we faced along the way of building one was, you can see, for those of you in the room, the telescope we were working with, it's the small, just trying to quickly, but this small 5-inch Explorer Scientific Telescope, it's a faded. But so obviously not designed for research. We were using a RGB CMOS camera that designed for making pretty pictures with astrophotography. Again, not designed for transit research, but we made the best of it. We made it work. We figured out tracking, autofocus, still sort of finicky there, but we were able, even with those equipment limitations, we were able to do real research, as you'll see. We dealt with, on the data collection side of things, we had to deal with meridian flips. So the mount that the telescope is mounted to can't flip over the meridian, so we'd have to stop imaging, recenter, realign, and then continue imaging. So sometimes there's like a gap in data. We had to figure out how to get all the settings right for research in SharpCap, which was very difficult and took a lot of trial and error. And by far the most important, the biggest setback that we faced was pixel saturation. So because we were working for with a 5-inch telescope, we had to expose our images for a long time to get usable data. Now, what happened with that is when we were imaging a bright star and exposing for maybe 30 seconds, our data would saturate and none of it was usable. And that happened a couple times. And sort of those setbacks and just like that trial and error of like, we think we detected an exoplanet and then we looked at the data and it was all saturated. That is what actually prompted my project, which I'm going to get into now. And then now I'll use. So this poster is the research that I presented at the Connecticut Science and Engineering Fair. As I said, my research goal kind of shifted. So once I identified actually how difficult it was for amateur astronomers like myself to break into this field and like start from nothing and try to do real research, I made it my goal to make it easier for not only myself, but all amateur astronomers to conduct real exoplanet research and make real discoveries. So to give some background, in recent years, exoplanets have become the epicenter of extrasolar study because they allowed researchers to understand the formation of planetary bodies, solar systems, and potentially even life itself. Exoplanets are often detected and studied using transit photometry, which is the method that we used to detect exoplanets, but also the method that the large funded like NASA sky surveys use to detect exoplanets. So it is not only an amateur method, but a professional one as well. So to conduct transit photometry, the researcher takes a series of images of a star with orbiting exoplanets to determine whether or not the star gets dimmer. Now, I sort of like to think about it like a solar eclipse on Earth. When the moon passes in front of the sun, the light from the sun gets blocked out, and then when it fully passes, the brightness recovers. Same thing happens when an exoplanet passes in front of its host star. Some of that light gets blocked out, and we're able to detect that. So just to sort of skip ahead to my results here, you can see a graphical representation of transit photometry here, where this is the initial brightness. This is the ingress period when the exoplanet passes in front of the star. This is during the transit event, and then this is the egress and baseline afterwards. So this method, as I stated earlier, you really only need a telescope, a camera, and tracking. If you can take pictures of a star over a period of time, you could detect an exoplanet. So clearly, detecting the exoplanet is not the hard part. As I stated, sky surveys can identify thousands of exoplanets in one go, but every single one of those exoplanets needs to be confirmed by several amateur astronomers like ourselves in order to be considered a confirmed exoplanet and for it to be studied. So my goal in this project was to create a user-friendly Python model to help amateur astronomers sort of break into the field and help detect some of those 8,000 exoplanet candidates. So the Python model asks for around 17 inputs from the user, all about observing conditions, equipment parameters, and I can show you the model later. It's on my computer, so it might be a little difficult, but I'll show you what it actually looks like. But once it collects those inputs, it outputs a graph shown here in figure 3. So there are a couple different components of this graph, so I'm going to take it piece by piece. But the most important aspect of the graph is this blue line here. So on the y-axis, it is minimum detectable transit depth. Transit depth is the difference between this brightness and this one. It's quite literally how deep the transit goes. And then on the x-axis is star magnitude. So essentially, this blue line, any exoplanet that falls above this blue line in this region here is detectable by the user. Any exoplanet that falls in this region is not. So for instance, if you had a magnitude 10 or an exoplanet orbiting a magnitude 10 star with a transit depth of, let's say, 7, this user would be able to detect that exoplanet. If it was a star of magnitude 14 with transit depth of 5, let's say, the user would not be able to detect said exoplanet. So that's sort of how the graph is used. The second important aspect of this graph is this red column that you see here. So this red column is indicating to the user that any star that falls within this magnitude will saturate their frame if they use 45-second exposures. So like I said, this whole saturation problem is what inspired me to conduct this research, so I had to include it on my final graph. But the way that saturation is calculated is by full width half max estimates. So everything that falls in this is, in the red bar, sorry, is with a conservative full width half max estimate. So it's sort of like a, okay, even best case scenario, these stars will saturate. These black X's indicate that the user should use caution when imaging objects that bright. So it's basically saying that, okay, if your full width half max is really bad, a star of magnitude, let's say 8.2, might saturate your detector. So it's sort of, it gives those two values to allow the user to have some more leniency and say, okay, if I really, really want a good data run, I'm going to be way outside of this region. If I'm okay with pushing it a little more, then maybe I can go into the caution. So do you guys have any questions about the output of the model before I move on? All right. Okay, so next thing I want to talk about is actually testing the model once I had it run. So I went to 2 different observatories, the Barnes-Bristow Observatory, where I conducted most of my research, and I also had the opportunity of visiting the John J. McCarthy Observatory in New Milford, Connecticut. At the Barnes-Bristow Observatory, as I said, we were using very amateur-grade equipment, but at JJMO, they have this beautiful 17-inch plane wave telescope attached to this SBIG camera, very much more expensive equipment they have there, research grade. So I was able to basically test it saying, okay, is this model usable for amateurs? Is it usable for solidified researchers? Which was very important because I wanted to get a range of values when I was actually testing my model. So the way I went about testing my model is I calculated the signal-to-noise ratios of hundreds of stars from a variety of different observing nights, using different telescopes, different cameras, different filters, really trying to vary the conditions as much as I could. And I took those signal-to-noise ratios, which are essentially just like a numerical value telling you how noisy your data is. I took that signal-to-noise ratio value and I converted it to minimum detectable transit depth using a very similar mathematical process that the model I created. I wanted to make the data as comparable as possible. So once I had those hundreds of stars, data from those hundreds of stars, I plotted here on the y-axis is the predicted value, which are the values that came from my model. On the x-axis is the experimental values, which are the values that I got from the two observatories, my goal was for all these blue dots to hug the 1-to-1 ratio line. That would show that my data collection was perfect. And it got really close. Numerically, there's a difference of around 0.68 parts per thousand, which for amateur astronomers is oftentimes more precise than it needs to be. So I was very, very excited about this result. Overall, it shows that the model is accurate enough to be usable and can help astronomers make real discoveries, which leads me into my next point of we discovered, I only have one light curve on my poster here, but we actually, I shouldn't say discovered, we detected 3 different exoplanets thanks to my model's output. So this first one is a very well-known, heavily studied exoplanet, HD 189733b. It's very large, easy to detect. We decided to start there because we wanted sort of a proof of concept. Like I said, it was the first time we'd ever done research with this equipment. We wanted to know if we could even do what we were trying to say we could do. We could. We had a very clean output for a transit light curve. I'm not sure if you guys are familiar with transit light curves. A lot of the time they're very noisy. It can be hard to even tell if it dips. Here, very clearly, there's a strong dip. What you can't see directly from this graph, but what we numerically calculated is that the period for the transit event as well as the transit depth aligned very closely with well-known values for this exoplanet. So overall, it was a very, very successful observation and a great sign that we could move forward. After that, like I said, we detected 2 more exoplanets, and the third detection is the one I want to talk about with all of you, because it was not actually a confirmed exoplanet when we went to detect it the first time. It is TOI 3885.01. That TOI stands for Test Object of Interest. And you'll notice how it's object of interest. It's not actually considered an exoplanet yet because we did not know if there was an exoplanet there. So I have the curve on my computer. I'm not sure if you'll be able to see it, but at the very least, those in the room can see that. Okay, perfect.
Backwards, but yes.
So you'll see that we actually did not capture the whole event the first time around because the NASA catalog told us that the event would be starting somewhere around here. Obviously, this was not true, so we missed a good bulk of it, but that also demonstrates that our research helped change, or hopefully will help change once it's approved and vetted, those published values and help make the information on this potential exoplanet the most up-to-date as possible. So this, the transit period, well, technically from this graph, we're not sure, but it's a fairly short period. I want to say it was around a week. So we are hoping to be able, weather permitting, to image this exoplanet several more times to get more concrete data on it. But so far, I mean, this graph in and of itself shows that amateur astronomers, even with our equipment, we can find data that does not exist. We can make true discoveries. So this was extremely, extremely promising for all of us. Finally, to sum it up, the next steps that I plan on taking with my research are to, on one side of things, I want to make my model even more user-friendly. I want to make it more approachable. It asks currently for, like I said, 17 different inputs. I want to help educate the user about what those inputs are, where they can find them, sort of make it less intimidating. And secondly, I want to continue to work to make my model more accurate. Like I said, it's a difference of around 0.68 parts per thousand right now, which, while it's incredibly accurate, it could always be better. And I hope to be able to use my model and test my model at a variety of different observatories. I know we've been talking to Westport Observatory about potentially imaging there one night. There are also more observatories up in Simsbury, where Barnes Bristow is. So yeah, I'm really hoping to expand my project, and I'm very, very excited to. The last part of my presentation that will probably be tricky because um, it's on my computer, but I wanted to actually show you all my model, what it looks like, and how to sort of play around with it. So I'll show it to the camera, but then also like I'm happy to pass around my computer so you guys can see it for yourselves, because I'm not sure how good of a view this will be. But this is my model. I use a program called Streamlit to basically take the raw Python code and make it readable and usable. So to sort of walk you through it, this drop-down menu on the left of the screen, my left, allows the user to select different cameras with preloaded data about each camera on them. I plan to, like, in the coming week, add maybe 10 more cameras to this list of the most used ones. So far, I have the ZWO ASI 6200, which is what we use at Barnes Bristow, and then also the ZWO Minicam 8. So as you can see, when I change between these cameras, these values for equipment-specific parameters about the camera change. Sort of to walk you through all the parameters this asks for. It asks for observing conditions, which include observing altitude, air mass, and sky brightness. If the user does not know these values off the top of their head, there's a little help button here that for every single input leads to either a map, a link, or a calculator that allows the user to, directly from the web, figure out what those values are for them. Then it asks for equipment-specific parameters, so the telescope diameter, as well as a whole ton of camera-specific parameters. Filter parameters, which actually people may not think about, but have enormous, enormous importance to observation. So whether you're using a Sloan Z filter we played around with, it depends very much what filter you're using to figure out which exoplanets you can detect. Finally, probably the most important parameter is exposure time. And then based off of all of these, it outputs a graph very similar to the one I have up there that tells the user which exoplanets they can or cannot detect. So I'm happy if any of you guys want to try playing around with the inputs. My computer's right here. Yes. But other than that, more or less sums up my presentation. I would love to hear any questions you have.
So you want to make this available, publishing it someplace?
So, as of right now,
Our code is for?
yeah, I do have to say the QR code on my poster is outdated. I have another one on the slide presentation if you're interested in looking at the code. Right now, it lives on a GitHub page, technically available for everyone to use, but I understand that not every amateur astronomer is going to browse GitHub pages to find what they need. So my ultimate goal is to transform this into a kind of real website or app to be usable by any amateur astronomer. If you search up exoplanets, my idea is that like you would find this app and then it would be very available for your use. But obviously that will take a lot of extra steps into formatting and less on the research side, which is the part I really love. But I do understand that it's necessary if I want to make something useful. Yeah.
And for your mentor work with exoplanet this section, are you familiar with that at all?
I'm not, but my mentor may be.
So this recommend that's the way that you can take your research and get it out in front of the amateur astronomer community.
Okay.
They do variable star observations. They record it for
Yeah.
scientific.
Not valid.
Yeah.
Your association of variable stars.
Okay. Yeah, I'm sure I encountered it. I know I've encountered the TESS initiative. They have. I think it's somewhat similar, but that's really interesting.
Webmaster for our website. Happy to post this for you.
Yeah. Next. Following your presentation.
That's amazing. Thank you so much.
And I also suggest you write a paper, send it to Sky and Telescope, which is now owned by the AES.
Yes. I have a paper in the works. So. Oh.
Jeff, is there an online question?
Hello, Jeff.
Sorry, yep, I was just trying to unmute myself. I don't see any online questions. I have one because it's hard to read from my screen. The graph on the bottom, so the actual, I guess, photometric data, does that
Yeah.
vertical scale start at zero or some number higher than zero?
Oh, okay, yeah. So, sort of the standard for light curves is to normalize. So, the y-axis is flux data, which is essentially magnitude, but slightly different. But it's normalized around 1. So, what this shows, it shows more directly like a percentage change in the brightness of the star, because yeah, so it's centered around 1 here, and it's normalized flux is what
Okay,
it's on.
okay. No, sounds good. Thank you.
Yeah.
That's Grace, all that mission.
No, I'm not.
Launches in September. It's about 6 months ahead of schedule, and they use mostly IR or infrared.
Yeah.
Right, straight, I'm sorry.
Okay.
Kind of replaced Chandra. 18 saltine tracker sized chips
Okay.
in a plane that's
Wow.
protected from meteorites or anything
Uh-huh.
else. It's going to be out in L2 where the web is.
Wow.
Yeah, so you might want to look that one up.
I will. I will.
See what research they're doing. And it's
Yes. I wonder where they're looking in the sky. I'll look at.
much more data than the current discovery.
Yeah. So this is Jeff again. I was on a private chat getting some info from Cynthia and treasury numbers, and I did miss there's a question from Bob Hammond. How many hours do you have invested into this very interesting project?
Absolutely. So, because I'm doing this research project through my school, there are some kind of norms that I should follow. So the expectation was around 40 hours a week over the summer. Um, yeah, no, it was quite a bit. I mean, like I said, we built the pipeline up from nothing. So a lot of that time was invested in figuring out how to align the telescope, checking why the focus isn't working, sort of that kind of work, which is very interesting for its own reasons. But yeah, so the expectation, 40 hours, maybe a lot of that was reading. Obviously, not all of that was data collection. Throughout the year, though, I've continued to meet with my mentor weekly. Actually, just yesterday, I was up in Simsbury to play around with some portable telescopes they have there, Dobsonian two-star alignment system. And yeah, very, very interesting stuff. But I've lost count of the hours, but it's been quite a few.
Yeah, just some quick math. It must be hundreds. Yeah.
I have a question.
Yeah.
Yes, so that was a wonderful presentation. It clearly shows how much background work you've done. And the question I'm about to ask probably has an obvious answer, but it's still kind of baffling me. So here goes. So say you are on a star, X number of light years away, looking at our sun to see whether this sun has a planet, and imagine that only Earth is the only planet it has. Now, out of 1 year around the sun, uh, Earth will be in front of sun only maybe for a few days. So how does one go about figuring out, you will have to have a whole year worth of observation to see a drop in intensity of the sun because Earth passed in front of it. So how is this research done on a larger scale?
Yeah, that's a great question, and that's actually a limitation of transit photometry. There are a couple, but there are many planets that have very short orbital periods. They're called USPs, or ultra short period planets. But so there are several that only take maybe a week to orbit their star. So very different from the Earth, but that allows for several imagings of the same planet to occur, which is what's necessary in order to confirm the planet. But I will say, there are studies that span over maybe 10 years trying to find, maybe they're trying to target planets in like the Goldilocks zone that we call, they're trying to look for life, and those will probably have longer orbital periods. So those studies can take many, many years, but the kind of research I'm doing now and the planets I'm targeting now, much shorter.
Okay. All right. Thank you.
Large majority of planets, exoplanets discovered now are what they call hot Jupiters, really large planets. Were out further and easier to detect with the light curve dips.
Yeah.
New missions like Nancy Grace Roman, for example, will help get them closer to the habitable zone.
So I'm trying to imagine like how you go about using this software. You
Yeah.
start out with like this long list of 8,000 objects of interest and look at your setup and say, all right, these are the ones I can look at. Or do you start out with an individual, maybe a handful of candidates, say, these are the ones I'd like to confirm. How can I change my setup or my situation to do that? What was your intention there?
So my intention was the first method that you suggested, that you first use the calculator or the predictor, figure out where you can target. I'll say, so what we used in our exoplanet study, Swarthmore College published a calculator essentially that you input your coordinates and what days you want to observe, and it will tell you exactly what transit events are on that day.
Who was that that wasn't the air mass. I saw Swarthmore.
Oh yeah, they also made a calculator for air mass, but so that was incredibly useful. It was a great starting point because it would tell us on a given day what would be transiting. So then from that much shortened list, not the full 8,000, you could then use the calculator, figure out in whatever period of time you want to observe which targets you should.
But as your data showed, they're
not always. So I've noticed that sometimes they'll forget to take a like TOI, object of interest, off of the catalog once it's been confirmed. So the data they'll have on the like object of interest catalog will be like 30 minutes off of the NASA catalog. So it is usually much more finicky and much more difficult to get a real observation because, as you can imagine, if they're like a couple seconds off the first time for the orbital period, then the next time it's like 6 seconds, then the next time it's 12 seconds, and then it just keeps compounding like that. So yeah, very quickly, big sort of shifts can happen.
Wow.
We have one more question and then we gotta move on. Is there anything else?
But just a comment.
Yeah.
You could be a millionaire. You start. Yeah.
Thank you so much.
Yeah, thank you.
Folks, this is Ishanvi, and she was a finalist at the CT Science Fair. Scott and I were walking. We go up and down the aisles because these kids jazz us. They're so enthusiastic, and they want to tell you about what they did because it's such hard work and good stuff. And we try to identify candidates by the category that the science fair runs, and the categories do not include astronomy, but they do include physical science. And in the physical science, we go and we look at anything that has to do with astrological activities, planets, exoplanets, space science, and so you get the idea. Under solar observation, we found this project and we said, well, okay, I took a look at it, and Scott and I scratched our heads and said, I'm not sure what she did. And so we had to get ourselves educated to be able to come over and talk to her. And when we talked to her, this room is full of people talking. And I have hearing aids, and I could hardly hear her, but I could see her enthusiasm. She's going to tell us about her project, but I need to tell you a couple of things to kind of prime you. It is, she's going to use a term CNN, convolutional neural network. And it's an algorithm or a methodology using machines in order to identify patterns in physical phenomena. And she uses that in a really creative way. And this is one of the things that so impressed us about her project. So would you like questions during your presentation, or do you want to take questions afterwards?
I mean, I'm completely okay with anything.
For
Really?
time we could do after, Bill.
Okay, so, but I think you're going to want to have clear, this is going to boil your brains, okay? This could be graduate level work. Serious, this is good stuff. Okay, go to it.
All right, perfect. Okay, so earlier this August, I started learning about what was known as the Carrington event, and that was one of the kind of biggest solar particle events that's ever occurred in human history. It occurred somewhere in northern England, and it was so massive that it actually caused, electrical power outages and even sparked fires in people's houses. And so that got me thinking, how dangerous really are these solar particle events, and what do they even do? And so in that research, I found that solar particle events not only have the capabilities of starting fires in people's houses, but they also play a lot more of a subtle issue in our day-to-day lives. They can tamper with our global communication systems, and they can tamper with our satellites. So I wanted to try to figure out a method to kind of solve this issue, or to help people become more prepared in order to kind of set up protective measures around their technology so that it doesn't influence them. And so that's where I created this project, a robust computational framework for solar particle event detection, where I integrated convolutional neural network, which is basically just like an AI framework that people use in order to, like he said, find patterns and to kind of classify different things such as images and things like that with multivariate proxies. Okay, so here's the background and context. So what are solar particle events? First, solar particle events are fluxes that occur due to disruptions in the sun's magnetic field. Basically, what happens is when there are disruptions in the sun's magnetic field, and when they come back together, it releases huge amounts of energy. And that energy kind of creates what are known as solar flares and coronal mass ejections. So coronal mass ejections cause a huge buildup of plasma and gases to occur, and solar flares are kind of a buildup of electromagnetic radiation and X-ray waves to occur. And so when these travel throughout space, they create something known as a shock wave, and that shock waves causes a lot of particle acceleration, which is what creates those solar particle events, which are fluxes of relativistic protons or highly charged ions and particles. And when these protons and highly charged particles hit our satellites, they hit our global communication systems, they have the potential to basically wreak havoc on them and kind of destroy them completely. So that leads me to the second issue, which is the sensor paradox. So you might be wondering, are there any current forecasting models that are trying to kind of detect when these solar particle events occur? And there are forecasting models such as Reptile and ProS to forecast proton flux. However, these models have two major limitations. The first is the sensor paradox. So during periods of extreme solar activity, the same particle flux that must be measured can saturate onboard detectors. And it's because these protons that are coming, they're relativistic protons, right? So they're traveling at speeds almost close to the speed of light. And so what happens is, this is a diagram of a transistor. And so you can see that this is an ionizing ion track that would kind of simulate the solar particle event. When it hits some of the p-n junctions of the transistors, the protons cause the electrons to basically fling off, and these can cause bit flips to occur. And when these bit flips occur, it can release null data, it can release corrupted data essentially to other communication or technological systems, and that can basically ruin the technology. And that basically also ruin the forecasting models. So the very proton fluxes that the forecasting models are attempting to kind of predict are actually being ruined by them as well. And then the second issue is that in order to predict whether a solar particle event is going to occur, you need to know the parameters, and you need to know the situation that can lead to a solar particle event. So there needs to be the coronal mass ejection needs to reach a certain threshold in terms of kinetic energy. There needs to be a certain shockwave, a certain magnitude of shockwave that needs to occur. The particle acceleration needs to reach a certain threshold. And so you have all these different parameters, but the issue is that they're so difficult to kind of measure with our current technology because it's happening in like this field of plasma. They're traveling at such high speeds that our current instrumentation cannot accurately like measure them directly. And so what happens is that many forecasting models need to, like, all these different features need to be inferred through complex modeling, which can create uncertainty and obviously inaccuracy. And so I thought, how is there any way to kind of evade this issue? And that's where the multivariate proxies come in. So even if you can't measure coronal mass ejection kinetic energy specifically, you can use substitutional variables such as, for example, velocity, which is a lot easier to calculate, that have proportional relationships to those features in order to determine like the relationships. For example, even if you can't calculate kinetic energy, but you know that the velocity of these particles, if you know the velocity of these particles, which is pretty easy to measure, and you know that there's an increase in velocity, well, that means that there's a direct proportional increase in kinetic energy. And so through the relationships, you can kind of figure out what is going on even with the features that we cannot measure directly. And that is what that is what the framework is also going to try to do, is to try to use the physics equations put in the substitutions of variables into these physics equations to try to figure out whether the parameters actually constitute a solar particle event too. So that is basically what the solution was. So the objective was to develop a robust forecasting methodology that integrates a CNN with physics-derived kinetic features to provide high-precision warnings. So instead of forcing operators to find blind when instrumentation saturates, this framework trains a CNN to recognize morphological pre-eruption signatures while pairing it with a multivariate physics proxy to validate incoming hazards using alternative and unclipped observation channels. So basically, a lot of current forecasting models are only able to detect the solar particle events when they are occurring. And at that point, it's kind of already too late because they're already undergoing and they're already getting exposed to our technological systems. And so what this does is it detects any pre-eruption indicators, like any indicators that a solar particle event could possibly occur in the future. And so what this allows is it gives us time to actually put up proper safety and protective measures for our communication systems, or even for our astronauts in space flight who may be in the path of a solar particle event and may be exposed to this high radiation. So these are the project materials and data sources that I basically used. I had to compile a lot of different data sets. The first and the main one was from Harvard Dataverse. This catalog listed every single solar particle event that occurred from 1982 to 2017. And this was, I'm pretty sure, between the solar cycles 21 and solar cycle 22. And so it has a lot of solar particle events. However, it's not just enough to give the CNN or like the convolutional neural network, which is basically supposed to mimic like a human brain. It's not enough to just give it the solar particle events, but you need to give it the parameters at which the solar particle events occurred at in order for it to recognize, oh, okay, this is the kinetic energy that you need for CMEs that translates to a solar particle event, or oh, okay, this is the particle acceleration levels that translate to a solar particle event. And so in order for it to make those connections, you also need a catalog of all those different variables. And the Harvard Dataverse didn't actually provide that. So I had to go to other databases such as the NOAA Space Weather Prediction Center, the NASA, a bunch of NASA catalogs, which provided basically CME velocity and angular width parameters. It provided X-ray flux and high energy proton flux acceleration and coronal shock frequencies, and all of these were kind of the features that I needed in order to tie it with like the solar particle events in order to feed it into the CNN. So that leads me to my procedure. So I basically did this project within 4 phases. Phase 1 was data acquisition and pre-processing, which is where I basically collected all the data that I was going to train my CNN on, and I had to create like the basically like the full data set. Second phase was the architecture development. I had to kind of basically engineer the hybrid computational framework consisting of a CNN for pattern recognition. Phase 3 was training and optimization. So for context, the way a CNN works, it's kind of like a child in a sense, because if you're trying to teach a child what a cat looks like, for example, you're going to give it a list or a series of images of a cat, but you also need to give it a series of images of non-cats, maybe tigers or elephants or things like that, so that it can tell what kind of anatomy, what kind of features a cat has and what kind of features like a non-cat has, like maybe a tiger or a lion. And so you're going to feed these images to a child. They're going to learn, they're going to gain the pattern recognition skills. And then you can test the child later by giving it images of either a cat or tiger and ask it to decipher which one is a cat or which one is not. That's also how a CNN works. So so in order to kind of accomplish this, I first had to give the CNN a list of all of like the solar particle events that occurred under what parameters did occur so that I could create those pattern recognition skills. And then and finally in phase 4, I tested the CNN in order to make sure that it actually knew what a solar particle, and it could actually accurately predict when a solar particle event occurred. So, but to get more into depth into phase 1, which is data acquisition and pre-processing, this first step involved compiling decades of historical solar event records, spanning from like 4 solar cycles, and then also raw multivariate time series records were synchronized across different spacecraft instruments, and I also had to align the time series strings for solar flares, CME velocity bands, and radio spectrograph charts. So these different catalogs of these different parameters like CME velocity, I had to figure out what times they occurred at in order to correspond them to the corresponding like solar particle event. And basically I compiled a fully fully furnished list of every single solar particle event that occurred within these couple of decades and every feature and like what the parameters were that under which it occurred with. So the phase 2 was architecture development. So this is where I actually created the convolutional neural network alongside an analytical multivariate proxy validation layer. So basically this kind of chart that you see over here represents like how this CNN actually works. There are 2 different validation layers to it. The first, so first you have the input tensor, which is where you give all of your data, which is like multivariate data of X-ray flux, proton density, CME speed, solar particle events, etc. Then you put it through path A. Path A is the inference engine, which is the CNN. This basically uses the pattern recognition skills because like before I had taught it what a solar particle event looked like. And so with those pattern recognition skills, it tried to predict whether under those parameters a certain did a solar particle event occur or not. After it got its answer, then the data moves to path B, which is the physics gate or the kinetic proxy. Here, I inputted all the data into a series of, physics equations or a mathematical framework, which is listed over here. And after it ran all the calculations, it tried to mathematically figure out whether a solar particle event could occur under those conditions. And then path B also tried to predict whether a solar particle event occurred or not. After you have what is like known as a resilience merge. So you basically like had the kind of the answers from both path A and path B merged. And if they do not match, if one says yes, a solar particle event did occur, and one says no, you have to go back and they have to try to refigure out what happened. And if they agree, then you pass it on, and then the output is given whether a solar particle event occurred or not. So that's basically the architecture that I developed. And so you might be wondering, how did I exactly solve the sensor paradox, which is that, just to remind you guys, that's when some certain like parts of the data are blocked out because the proton flux has kind of overwhelmed the technology. And what I did was I injected synthetic data gaps into the training data set. So I trained my CNN on incomplete data so that it could kind of like get used to or make sense of gaining pattern recognition skills without having the entire full data set at their disposal. Because in the real world, there are going to be moments where, when a solar particle event occurs, the technology is going to be overwhelmed and they're going to be missing some data. So I want to simulate that kind of real life experience when I was training my CNN. And so that's basically how kind of I overcame that issue as well. And so I mimicked the physical clipping and amplifier saturation profiles seen during massive solar storms, so the CNN was prepared for any type of problem or issue that could occur. So this is phase 3, which was training and optimization. So after I had constructed the CNN and after I acquired all the data, now I needed to teach the CNN what a solar particle event looks like. And so this is where I kind of fed the data to the CNN. But there is one issue, because in history, there have been a lot more non-solar particle events than solar particle events. Like I said before, there were only like 342 solar particle events that occurred from the span of 1982 to 2017. However, there were like thousands of more timestamps that didn't have any solar particle events. The CNN model was biased towards kind of predicting that, oh, there was no solar particle event occurring every single time because it knew that probability-wise, if it guessed, it would have probably gotten it right, just because of the overabundance of non-SEP events in my data set. And so kind of to mitigate that issue of the CNN just guessing rather than actually applying proper logical thinking skills, I use a technique called SMOE, which kind of mathematically inflates the minority data set, or in this case, the solar particle event data set, of historical solar storms, preventing the model from becoming biased towards quiet conditions. So basically, I raised the amount of solar particle events that occurred from 342 to around 600 or 700. I artificially created like completely new solar particle events that never actually occurred, and I created like parameters for it that would realistically mimic what happened during real life, in order so that it had like an equal set of non-solar particle events and solar particle events to train on. And so after that, I went through multiple processes of like kind of training the CNN on these different data sets. And then finally, we get to phase 4, which is the performance and benchmarking. So after I've taught my CNN what a solar particle event looks like or under what parameters it would occur under, then now I actually have to test whether it actually learned anything from what I was teaching it. So I did this by separating 47 high impact historical solar storms that actually occurred that I didn't use in my training set. So it's never been exposed to these solar storms. And I tested, and I also included a bunch of non-solar particle events as well to see whether it could accurately find and locate all of those 47 solar particle events. So this predictive framework was benchmarked against historical baseline outputs to measure lead time gains as well. And so we can see that the results from this in like my statistics summary, which is that it ended up having an accuracy of 89.4%, a precision of 90.3%, and an average lead time of 25.1 minutes, which is like half an hour before a solar particle event were to actually kind of impact any technological system or our satellites. So this is the multivariate proxy, the kinetic proxy inference. So like I said before, there are 2 validation layers. You have the CNN, which is basically using its like pattern recognition skills to kind of determine whether a solar particle event was occurring. And this is the second layer, the second validation layer, which kind of checks the work of the CNN. So these are the equations kind of I used, or some of the equations I used. I used the plasma frequency equation. So it uses electron density to determine shock wave starting altitude based on initial radio burst frequencies. I used a velocity inference derivation, which basically used the drift rate of the particles and density scale height to kind of infer what the magnitude of the shock wave was. So basically, if you know the drift rate of the particle events, you can kind of figure out through this equation what the magnitude of the shock wave was. And if you know what the magnitude of the shock wave was, you can know whether it was like a good condition for a solar particle event to occur. And then this was the propagation delay calculation, which basically calculates like the time gap over a distance between the light speed radio signals and the protons themselves. And so the network basically acts as a visual differentiator. By matching spectral drift slopes to true speeds in the validation data set, the framework predicts particle arrival times before the protons even reach orbital sensor hardware.
So is this a multivariate proxy physics-based model that you use to create those fictional events that you use to train the neural net?
So the synthetic solar particle events that I used were kind of different because there's 2 different layers to my model, right? The first layer is the CNN. CNN is trained on a specific data set, and some of that data set I artificially created. Once it's trained on that data set, it makes a prediction based off of its current knowledge. But then the second layer is the multivariate proxy. It's completely separate from the CNN.
So you're creating the fictional events implies you have a physics-based model, and I thought that's what you're getting into here, but there's something else you got.
No, yeah. So the SMOE technique that I use basically takes actual solar particle events that occurred and check like what range of like values the features are under. So for example, if the semi-kinetic energies are between like, X joules and Y joules, I would artificially create solar particle events with kinetic energies in between that X and Y range. So I basically kind of just use the ranges that were given by the actual solar particle events in order to create the synthetic in order to create synthetic new events. However, in this kinetic proxy secondary validation layer, I basically use what it does is it takes the data that's coming in from like space and it plugs it in through these different equations to figure out like the parameters at which the solar particle event is occurring, such as like the burst frequencies, the shock wave magnitude, and the temporal gap in order to ensure that a solar particle event is actually occurring or not. So the first one uses pattern recognition skills. Then the second time it checks the logic of the CNN and it double checks it by going in and checking if the physics actually makes sense.
Basically a test situation.
Yeah, it's like a test. It's like if you had one teacher, grade your test, and another assistant teacher could also probably grade that test just to make sure that the first teacher didn't grade it wrong. And so that's what kind of this physics model does. It makes sure that the CNN didn't get anything wrong. So this was my final model performance summary that I mentioned before. I ended up getting a classification accuracy of 89.4%, a precision profile of 90.3%, then a 93.3% sensitivity recall. And you can kind of see, you can probably visualize these numbers better through the confusion matrix. So this basically shows you the amount of true negatives and true positives that occurred. So out of the 30 actual solar particle events that I gave it, it was able to accurately predict, it was able to spot 28 of them. And 2 of them, it ended up labeling not accurately as there was no solar particle event. And then out of the 17 non-solar particle events that I gave it, it ended up accurately identifying 14 of them as actually like non-solar particle events. And so, you can see with this confusion matrix that it was a pretty accurate and like reliable model that we could possibly implement in the future. However, obviously the numbers can increase as well. And then we can see that the average alert lead time was 25.1 minutes. So this basically tells you that the model is able to predict when a solar particle event is going to occur 25 minutes before it actually reaches the technology in itself, which is a pretty good lead time, especially because it's enough time for people to set up their proper protective safety measures that they need to, shut down any communication networks that they need to, and stuff like that. And it also gives, for example, if you're on a space flight and a solar particle event is occurring, it gives the astronauts proper time to put on protective gear or to move to a part of the space shuttle that is protected from this high radiation.
So it's fun. This is an current frame, right?
Yeah.
Currently it's what, 20.1 or something like that?
So right now, forecasting models can't predict the solar particle events before they actually occur. They always how they work is that they intercept them when they actually occur. So this one is actually an improvement by 25 minutes because originally they would predict them at the on-site of the solar particle event. However, there have been other models that I've seen online that are similar to my logic that have been able to do it within 10-15 minutes or even 20 minutes. So this is also an improvement by 5 or 10 minutes from those even as well. So these are my project challenges and reflections. So the first thing was the accuracy paradox that I was telling you guys about, which was basically the model initially showed a misleading 96% baseline reliability and accuracy because in my training data set, I had a huge overabundance of non-solar particle event data compared to solar particle event data. So the model ended up just spamming again and again non-solar particle event without actually checking the logic because it knew that since most of these are non-solar particle events, it could probably just guess and probably get it correct. And so in order to kind of fix that issue, I did the SMO technique, which kind of balanced the data set in order to have an equal amount of solar particle events and non-solar particle events. Then there was the issue of the sensor blindness, which is what a lot of forecasting models today fall prey to. So to make sure that my like CNN or like my model doesn't kind of have any performance anxiety or doesn't like it doesn't stop working in real time, I made its training process a lot harder by like injecting synthetic data gaps or taking out some of the data that I used to train it so that it could properly like so that it could properly understand how to predict a solar particle event even under the conditions of not having all of the data that it needs. And then bypassing the telemetry gaps, the custom computes a kinetic shock proxy using CME velocity and radio burst, while the CNN simultaneously analyzes the proton flux sheet to maintain detection capability. So basically what it's saying is that the physics-based kinetic proxy is like a secondary validation layer that double checks the work of the CNN to make sure that it can be as accurate as possible. So project improvements. I would say the first thing is to shift the project from a CNN towards an LSTM architecture, mainly because a CNN is mainly used for image recognition, which means that it's best at like taking images and finding patterns within images themselves and then trying to classify images. However, an LSTM architecture is good for time series data, which was what I was working with in this project because I was trying to feed it time series data, historical data from different timestamps of solar particle events. And so for that, an LSTM architecture would be better equipped to handle that. I would also, instead of using SMOTE to kind of artificially increase like the number of solar particle events, I probably used GAN or which is kind of like another AI algorithm that is used to kind of generate new things such as like solar particle event data and stuff like that instead of the SMOTE because it would probably be way more realistic and just way better for this project in general. So future plans. Right now, like first what I would do is like transfer it over to the LSTM kind of algorithm, but also I would want to kind of connect, like, because right now what it's working on is like historical solar particle events. The next step, obviously, to this would be to connect it to an actual satellite so that it can process real-time data that's coming in from satellites in order to kind of predict whether a solar particle event is occurring. Because right now, it's been able to predict historical data, but it hasn't actually been used in real time. So what I would do is probably connect it to like a satellite like Discover or ACE at the L1 Lagrange point. And so this kind of expands predictive horizon and allows for cross verification of incoming CMEs. And it also just helps check whether the model is actually able to handle itself during like actual events that are occurring. I would also implement temporal forecasting. So by replacing static snapshots with like an LSTM architecture, and then I will also like probably automate the dataset optimization part of it. Instead of kind of the way that I like put together all of the data into one consistent data set took a long time and it took a lot of memory and energy. Instead of that, I would probably develop an automated framework to dynamically rebalance the data as new solar events occur, which helps maintain like the model stability without overreacting to minor fluctuations. Okay, that's pretty much my presentation. But I'd love to take any questions if anyone.
Just a quick one. You stopped at like the SDO and then Carlisle down at the end there. Did you solar probe come into the cell?
Sorry, the what?
Parker Solar Probe, the latest launch for solar.
At the time when I was like making the project, I didn't really consider that because I mainly just like thought of connecting it to current like satellites that I knew of, which was like the Discover satellites and the ACE satellites. So I didn't actually consider that, but I would love to read more about it and see if
Launched a couple of years.
Yeah.
Hi, there's a question online from Richard Moser. How much did you rely on NASA SDO data and or synthetic data, and how did these impact your model?
So the NASA I basically use the Harvard Dataverse for the actual solar particle event data, but then obviously that's not the only thing that because I use the NASA data for like the features or for kind of like the conditions under which this solar particle events occurred. So I use it for stuff like the CME velocity. I use it for the proton fluxes. I used it for like the radio burst energy levels, and those were kind of like the conditions or the parameters under which the solar particle events occurred in. So that's mainly what I used it for, but I didn't actually use the NASA data sets for any of the solar particle events specifically. As for like how much did I artificially inflate the data set? I had to pretty much like double the amount of solar particle events that I gave it, which was like 300. I like pretty much double that to like 600, just because, you know, when you look at like the timestamps that I was giving it, there were so many more non-solar particle event data that I was feeding it compared to like the 300 solar particle events that I was giving it, because high intensity solar particle events don't occur like that often. So I did have to inflate it by like 2 times in order to like kind of rebalance the data. However, that doesn't necessarily mean that it's not accurate, because again, the artificially created solar particle event data that I created was based off of actual solar particle events. So it uses the parameters of actual solar particle events to generate new ones that would still theoretically be feasible in real life as well.
Okay, thank you. So this is Jeff. Actually, I've got a question. So I do try to see Aurora Borealis when it's predicted. So I am familiar with the Space Weather Prediction Center from NOAA. So they do give predictions just of, possibility for auroras and aurora sight lines. Just in broad brush strokes, how does that differ from what you're doing, which seems in some ways much more exact, shall we say? Could you describe that a bit?
Yeah, so I think the conditions under which like the northern lights and this were to occur are kind of different, because solar particle events are a lot harder to forecast because they occur pretty far away. They're incredibly high energy, high speed. They occur under this like a bunch of gases and a bunch of like plasma, and so that's why it's really hard to get like accurate data on it. And so I think that's one of the reasons why like predictive forecasted models are kind of hard to make. The reason why mine might also seem like a little bit more like technical or a little bit more accurate is because I did run it and test it on like confirmed data from like historical data. So all the data that I used on it was like it was also like verified, it was run through, it was like it's already been like established, it's already been established in data sets, it's already been cleared through like proper instrumentation, and the solar particles themselves have also been vetted for. And so it was given a very clear cut like data set to work off of, which also might contribute to why it's able to predict them so cleanly. But again, I would have to connect it to an actual like real life satellite, or I would have to connect it to like a real life stream of data in order to ensure that it can actually properly take in like real-time data from space and accurately make predictions off.
Okay, thank you.
So Bob Hammond asked, what are your plans after high school?
My plans after high school. Oh, well, I'm a junior, so that conversation is very talked about frequently. But I've always wanted to combine, going into astrophysics with like computer science or mechanical engineering. I've always been interested in like the coding aspect of astrophysics, especially with like using statistical models to, analyze cosmological data and stuff like that. So it would be very similar to the work I'm doing now, just probably on like a bigger level with hopefully more resources and funding and stuff like that.
Thank you.
Know what your dad does for a living. I can't imagine the conversation around the dinner table.
What do you do for a living, sir?
I'm in technology as well. I'm a software developer as well. So,
Yeah.
the reason why she picked up the neural network is because the prior project she did was on the images.
Yeah.
Yeah. So there was a project in eighth grade. It was like classifying lenticular galaxies through a CNN, which is why I picked up a CNN for this product, because that was the framework I was most
Yeah.
comfortable with. But again, like I probably like transferred to an LSTM this time, just because it fits better with my project. But I'm pretty familiar with CNNs.
So you guys are, you get a sense of what Scott and I have to deal with.
Yeah.
No, take a look at the science. Both of these projects really depend heavily on computational science in order to be able to extract meaningful data that pertains to space science or astronomy. And this is the stuff that's approachable now at the high school and undergraduate levels. Very powerful artificial intelligence, neural network types of things. Beyond, basic HTML and basic programming, right? It's a little bit past that, I'd say.
And with the internet, I mean, with GitHub and things like that, there's already been so much like code that people have written on this kinds of thing, like CNN architecture that's already been developed, that's public and available for use. So it is really a lot easier now to do something like this.
That smoke technique is a statistical technique that's used a lot in the insurance business, especially. Yeah. So
Also, like, one thing that I realized, and I wasn't aware of it, is like, Google allows you to have access to all these CNN networks free of cost. The entire GPUs, at least like, it makes it available for almost nothing. Like, it was all free. Probably if you spend $20 a month, would even give you, pretty powerful machines that are at your disposal.
And one other thing, since we met, the Artemis 2 went up, right? And there was a CME that NASA was very concerned that it would the spaceship would intercept the CME. It did not. Everything was fine. But this is space exploration, cutting edge space exploration science. So very good stuff. Thank you very much. Oh, and Scott gave Mia hers, but this is a little thank you gift.
Thank you so much. I really appreciate it.
So, and you guys are members too, by the way. You're members of our club.
Yes, you are.
Thank you so much.
It's all about the wording, so you gotta be careful when you say things.
Yeah.
All right. My turn.
Okay. So our next meeting then is September 16th. I'm looking at a calendar. That's the third Wednesday in September.
In September, yes.
Indeed.
Okay.
Well,
And in the meantime, the couple things that were mentioned, these outreach events and you'll reach out, Chris or Dean, if Van Vleck gives some dates to those who signed up.
yes, I will.
Okay. Okay, great.
Yeah. Straight something if it's not, if it's
No,
friends, right?
no. I've heard.
I'm gonna be a Stella fan.
I've already read that.
I forgot all about it. It's on. But Dick's gonna go. Dick Moser.
Is he?
Yeah. 30% chance of rate. It's gonna be locality for the most part, but they'll still be promoting us and. Yeah, okay. Just let's find out. Because I told him I would. All right.
You told me.
Asked.
Oh, yeah.
Because I told him I sent it to you, but I stupidly forgot to put it on my calendar and made other arrangements.
Yeah, no.
Okay.
I
I'd like to make the motion.
oh, sorry, I just want to say one.
Please.
That's kind of you guys are doing a fantastic job of finding the kids to present. Wow. Knock my socks off, both of them.
Amazing.
Yeah.
So
Oh my gosh.
what happened to me is something that maybe we can help. Early March, they have the first round of evaluations for the science fair. They don't have anybody that has astronomy chops. to be able to help advise any of the judges or be a judge for astronomy projects or space science projects. Because they focus on the biohealth projects.
Like, I'm thinking, this would have been, this would have been Cynthia Peterson's kid. You know, like,
Astronomy, it's not even part of the core curriculum. And that's why they focus on it.
Right.
And that's why Scott retired from teaching.
So come March or in February, we can come back to the club, and I'd like to recruit some more members so that we can go and evaluate some of these things. We can work with the science fair people and try to sit for projects that are space science and astronomy related. If you really want to take it up a notch, we can sponsor an astronomy category. Now, this is the way that you incentivize projects that focus on space science and astronomy.
What would that entail?
About $3,000.
Well, it's certainly worth it. I mean, especially if Scott's behind it. He was certified teaching.
Yeah. So Scott, we were just talking about the science fair, getting judges in at the first round, and then if we want to take it up a notch, sponsoring a category.
Yes, yeah. But we'd sure like to see some of our club members drop by and just see what it is we do and the way the place is set up. It's really
I'm scared.
That's amazing. It's amazing.
There are a lot more where they
I mean,
came
they
from.
have, they teacher advisors, it's not like they would be looking to us for technical knowledge.
I don't know about that.
So not so much that, but the challenge is the people that are sitting as judges are not versed in these physical science, in space science, astronomy in particular. When she was talking about variable star, measuring the light profile, these other guys can draw blanks. They have no idea. And so
Something is
I
basic.
think people that understand that
That's hardly basic anymore.
will help promote some of these products.
What kind of credentials do you need to be in that judging?
Well,
Like,
a former NASA solar system ambassador or a current NASA system ambassador, what better credentials other than
I
a
don't-
teacher?
When you become a judge, you are
Even
presented in a way. See what your background is, what you do. We also go through a security check through, what is it, Sterling or something?
My qualification is I'm a stat scientist and an amateur astronomer. That's the qualification they allow. Well, of course, we're a special award too,
Yeah,
but they'll let
so
us in, I'm sure.
there's a lot of wiggle room if you're in special awards. I mean, a lot of special awards come from the local, Pratt Whitney, Hamilton Standard. Some of the other companies in Connecticut will sponsor an award, a special award. And there is a special award ceremony that happens on the Saturday after the event, which the judges are invited to. I've never been able to make one. But these two attended that ceremony and received our awards at that event. That's how it's handed off. And they are so excited about it. They get excited if anybody will listen to what it is they're doing. So you can, at first to see it, and after a while, you can feel it. It's really something. But these two were just, I mean, every time I communicated with them several times. My last communique was yesterday. Oh, by the way, this is an informal event. Jeans and a nice top will be fine. And they both said, "Thank you for that!" Exclamation.
Oh,
But I digress. If we could get a few club members to come in and share the experience with us, that would be great.
this was 15 years ago, kind of 4 or 5. We had Parker from Pratt and Whitney, Tom Hoffelder, Julian Scholl from Otis. These guys.
Well, Al, but in a number of years.
Yeah.
6'5" would it be?
Yeah.
So we can take this as next season, we can put it on the agenda towards the end.
Well, we should do it now. It's a new business item
Yeah,
because that's a significant amount of money, and that gives the summer for you guys to talk about it.
right.
And I make a motion, we entertain the idea of sponsoring an award at the Connecticut Science Fair,
Science fair.
Connecticut Science and Engineering.
Science and Engineering Fair. And I'm saying we do it so we entertain.
I second
Okay.
the motion.
Entertaining discussion, was that?
Thank you.
That means that we can look at it rather than preclude having money right now. I mean, let's talk about it. We
One
got
quarter,
speakers.
first and second.
Yeah, we're in discussion.
Okay.
It's like,
Can
So-
somebody shoot me an email with the right words for that for the minutes?
I make the motion.
We have to vote.
Yes, of course. Motion seconded. We had the discussion.
All in.
Any further discussion? I did not put a dollar figure on it.
I say we talk about this in September and then vote on it in like October, November.
It's the plan.
Okay.
All in favor?
Aye.
I
Aye.
This was agenda item.
Okay.
That's what this motion really is. And we have all summer to gather brain trust.
Sounded like a pass to me.
Well,
Oh, any opposed?
We are gonna get kicked out in like a minute.
yeah.
Nobody's opposed. Motion carries.
The other thing
Yep.
I'd like to say, the speakers you brought in this year.
Oh, great job.
Yeah.
We get them all.
Thank you.
I move to adjourn.
All in favor of
Second.
adjourning?
Aye.
Yeah.
Aye.
Do it all night.
Whatever the order was there.
Oh, what
Aye.
what we.
Thank you, everybody that's not gonna be here until September, have a great summer.
Can I help you with this?
It's your phone.
You too.
Can I help you with
Bye.
anything? Camera,
Aye.
system?